My name is Mike DeVacluse, President of Lesman Instrument Company. I'd like to thank all of you for taking time out of your busy schedules to join us for Load Cell Basics. Today, Jim Heaphy, Sartorius Intec's National Sales Manager, will teach you about the basics of load cells for level by weighing applications. Jim joined Sartorius Intec as a tank and hopper specialist in early 2015 and currently serves as National Sales Manager. Prior to that, Jim spent 10 years at Avery Weightronics as a technical account sales manager. Over his career, he's also held sales and service positions at companies like SPX, GSE, and Controlled Power, and served as a U.S. Navy electronics technician for 6 years. He will cover what a load cell is and how it works, reasons to use load cells, different types and styles of load cells, the benefits and shortcomings of each, how Sartorius solves typical load cell measurement issues, some application success stories. Just in case you'd like to view the presentation or share it with a coworker, the presentation and slide deck will be published on our website in the next couple of days. We will be muting all the phone lines. If you have any questions, there is a question tool built into GoToWebinar. Please send me the questions and I'll get them answered. With that, I'm going to turn it over to Jim.
Thank you, Mike. Good morning, everyone. Mike did a great job of introducing me. I've been in the scale business for a number of years, so I'm certainly hoping that my experience can help everyone understand and get a better grip on how load cell works and which one is to choose for the right application. This presentation will take approximately 3 hours, so I hope everyone brought their lunch with them today. No, that's kidding. We're probably going to keep it down to about a half an hour, and I do appreciate the time out of your day today to go through this with me. Let's go ahead and get started. We've got many types of load cells available on the market. Today we're going to go over resistive load cells. They come in many different designs. Each type is tailored to its specific need. Canister, S-type, compression, shear beam, and specialty load cells. Today we're going to focus on shear beam and touch on canister and compression cells. Let's start a discussion with the most common weighing element, the strain gauge load cell. This is the most common load cell used in the weighing industry. It can be found in bench platforms, floor scales, and in some cases, tank and hopper systems. The most common electrical strain gauges are thin, rectangular-shaped strips of foil with maze-like wiring patterns on them leading to a couple of electrical cables. You stick the foil onto the material you want to measure and wire the cables up to your computer or monitoring circuit. When the material you're studying is strained, the foil strip is very slightly bent out of shape, and the maze-like wires are either pulled apart, so the wires are stretched slightly thinner, or pushed together, so the wires are pushed together and become slightly thicker. Changing the width of a metal wire changes its electrical resistance because it's harder for electrons to carry electric currents down narrower wires. So all you have to do is measure the resistance, typically using a Wheatstone bridge, and with a bit of appropriate conversion, you can calculate the strain. If the forces involved are small, the deformation is elastic, and the strain gauge eventually returns to its original shape. So you can keep making measurements over a period of time. Stress and strain. Stress is the measurement of how much internal pressure a material is under when a force acts upon it. The bigger the force or the smaller the area over which it acts, the more likely it is that that material is just going to deform or change shape. Just like pressure, we measure stress by dividing the force that's acting on it by the area it's acting over it. So stress equals force divided by area. Strain, on the other hand, is what happens as a result of stress. If a material is stressed by force, it often changes shape and gets a little bit longer if you pulled it apart, or shorter if you pushed it together. The strain is defined as the change in length the force produces divided by the material's original length. So if you pull a 10 centimeter long piece of elastic and it stretches by 1 centimeter, the strain is 0.1. In a bar strain gauge load cell, the cell is set up in a Z formation. So the torque is applied to the bar, and the 4 strain gauges on the cell will measure the bending distortion, 2 measuring compression and 2 measuring tension. When these 4 strain gauges are set up in a Wheatstone bridge, it's easy to accurately measure the small changes in resistance from the strain gauges. As you can see, when they're configuring a lead stone bridge with 4 separate resistors connected as shown in a network, an excitation voltage, usually 10 to 12 volts, is applied to one set of corners, and the voltage difference is measured between the other 2 corners. At equilibrium with no applied load, the voltage output is 0 or very close to 0. When the 4 resistors are closely matched in value, that is why it's referred to as a balanced bridge circuit. When the metallic member to which the strain gauges are attached is stressed by the application of a force, the resulting strain leads to a change in resistance in one or more of the resistors. This change in resistance results in a change in output voltage. This very small change in output voltage, usually about 20 millivolts, a total change in response to full load, can be measured and digitized after careful amplification of the small millivolt signal to a higher amplitude of 0 to 5 or 0 to 10 volt signal. These load cells have been used for many decades now and can provide very accurate readings, but require many tedious steps during the manufacturing process. Once again, the strain gauge is a device that measures electrical resistance, changes in response to the proportion of strain or pressure or force applied to the device. The most common strain gauge is made up of very fine wire or foil set up in a grid pattern in such a way that it's linear change in electrical resistance when strain is applied to one specific direction. Most commonly found with a base resistance of 120 ohms, 350 ohms, or 1,000 ohms. Excuse me. Each strain gauge has a different sensitivity to strain, which is expressed quantitatively as the gauge factor. The gauge factor is defined as the ratio of fractional change in electrical resistance to the fractional change in length. The typical gauge factor for metallic strain gauges is typically around 2. Advantages of shear beam and bending beams. Also, one of the advantages, the advantages are going to be low cost, can be used as a structural member of the scale, and works well in floor scales and bench scales. Disadvantages of bending beams. All cells have a slightly different output. If the tank has a side load, the output will change because the cells are not matched. If a cell is replaced, the system also must be recalibrated. Junction boxes require trim pots when the cells aren't matched to balance the load. This adds a weakness to moisture infiltrating the box and causing erroneous signals. Every calibration is unique and must be done by spanning a mass, meaning you must apply full load to the scale in order to completely span and know what the millivolt signal would be back to the digital indicator. And most importantly, not optimized for resistance to creep. They have inconsistent metallurgy. Tanks have a constant load, not like a bench scale that is loaded and unloaded. Not optimized for drift. Inconsistent gauges. You can have a lower millivolt per volt output signal, creating erroneous signals that way. Most importantly, in a shear beam load cell, when used in a tank application, is any force applied to that load cell, whether it be vertical, horizontal, or any kind of rotational torque, is all applied to the cell and will cause a change in weight value. Tank cells and mounts need to meet a much higher standard. Tanks are difficult to measure with a mass. It's very hard to hang weights or set weights on top of a large tank or vessel. Tanks also face motion, side loads, temperature swings, and require exceptional linearity and resistance to creep, because you're going to fully load a tank and it's going to sit there with the same load for days, weeks, or months on end. Tanks are often called on to higher precision. They want to know a much higher resolution of what product is actually in the vessel. Tanks used in processing can cause tremendous financial loss when there's a failure. They want to know exactly what's in that tank at all times. We talked about before real quick, going back to facing motion. One of the most important things in a tank is that tank may be jacketed, so you're going to have heating and cooling, and you're going to have expansion and contraction. And we're going to cover here later in this discussion exactly what I mean by allowing movement but still maintaining control of the vessel. Shear beams are good for use in tanks and silos when the product has low value and precision is not necessarily a big deal to the customer. The time lost in production has no value, and potentially if you have to wait for a new load cell and then do the calibration of that new mass, If you have the time and the product is not terribly valuable, then load cells, or the shear beam load cell, is perfect for this application. The canister style load cell. It's the earliest load cell design. It's either hermetically sealed or welded to protect the gauges. There are two types of canister construction. Single column, which is what you see here, and multiple column. Single column canisters cannot normally withstand a side load of over 15%. Multiple column canisters can withstand more side load than the single column variety. The canister cell ranges in size from 100 pounds up to 500,000 pounds. The normal safe working overload is 150% of full scale. Some models can withstand up to 100% of full scale capacity before any damages occur. Due to the fact that I work for the manufacturer, I get to promote our products on at least one slide. This is the one that I choose. The ridge mounting of the shear beam on top virtually assures that all torque forces will be transmitted to the load cell and interpreted incorrectly as weight values. Any movement, either horizontally, uplifting, or circular torque, will be sensed as erroneous weight values. Due to the unique top and bottom curvature of the Sartorius Intec compression load cell, the more side force applied to the cell, the more restoring force it exerts back to remain vertical. Example, the kid's punching a toy that always attempts to right itself. The example on the right shows the load cell installation that has been severely shifted out of position, but the load cell is still seeing the vertical force representing the weight as it pushes the tank vertically due to the curvature on the top and bottom of the cell. The load cell remains the same height as the tank tilts due to the increasing the length of the load cell as it rocks on its axis. Design. When it comes to the canister load cells, each cell must be made perfectly. Identical perfect alloy, perfect gauge manufacturer. Gauge attachment is perfect and consistent. Low signal output reduces creep. It's got a very small millivolt per volt signal, 1 millivolt versus 3. Less compression. The cell will only deflect 0.5 millimeter at full scale. Temperature compensation over entire range of output and operating ranges. Most importantly, exact millivolt per volt output for each cell from the first cell manufactured until today. Benefit, all cells can be replaced with no calibration. Output never changes with side load, motion, time, or temperature. Impervious to water. Calibration is accurate without spanning a mass. And incredibly intrinsic resolution and accuracy. Okay, one of the requirements of the electronics must be able to amplify a very low current signal from a load cell and be linear and drift free. Must have an A to D capable of very high precision. Must be able to communicate with process controllers, or must be an industry standard process controller. Resolution. Most instruments are designed to be legal for trade, 5,000 to 10,000 divisions from a 3 millivolt per volt signal. At 10 volts excitation, a 5,000 division sensitivity would be 6 microvolts per division, which is typical response for an inexpensive instrument. Many instruments can resolve half a microvolt per division. The highest resolution for an analog strain gauge is 7.5 million divisions from an 8-volt source, or 0.003 microvolts per division. Load cells in groups of 3 to 6 constitute a single analog scale. What we mean by that is with perfectly matched load cells, trim pots are not needed, so a junction box needs to be provided to sum the signals for instrumentation. The box must be resistant to signal changes caused by moisture and also be highly resistant to moisture. Load cell cables need to be capable of transmitting extremely weak signals without distortion caused by inductive or capacitive reactance. Load cell and home run cable must be impervious to water ingression as well as resistant to UV, cracking, or stretching. We recommend a PTFE coating with Kevlar center and separate shielding on the signal wires as well as a triple shielding overall. This will reduce noise and produce a much cleaner, very small signal back to the instrumentation. Okay. Mounting kits when choosing for a tank assembly. They must be designed for use in the process vessel and silo weighing. That's where the canister load cell mount that you see before you today has been designed. They're highly accurate, made of milder stainless steel. They have huge capacity ranges from 500 kilograms up to 300 tons. Designed for horizontal forces from 25 kilonewtons up to 200 kilonewtons. And vertical forces from 30 kilonewtons to 250 kilonewtons. Key to the sensitivity of quality load cells is side forces. Is the built-in constrainer system These constrainers, sometimes called check links, let me do this right here, keep the tank from twisting exactly where the force is most critical, directly at the load bearing point of the load cell. While external tank constrainers can serve the same purpose, they may hold the top of the tank while the bottom continues to move. It's always best to restrict tank movement where it counts the most, at the point of weight determination. Typical constraining mounts are easy to install and can be less than 2 inches tall. Removing the cells equally simple and requires only turning of the bolt-in jacking bolt, turning the built-in jacking bolt with simple hand tools. The load cell mount can be the weakest link in a tank or silo system. Ensure the mount has been tested and is capable of withstanding all environmental forces the system could experience during operation. Specialty mounts, like the ones you see before you here, are available for markets for specific applications. The seismic mount is designed to be used in areas that are known to have high propensity of seismic activity. As you can see, there are many areas of the U.S. that require special considerations when designing a tank or silo system. All load cell types offer individual range of mounting kits. The kits vary in their capacity of force and compensation. Inside installation is where you have an earthquake risk. That's where you have to determine if you need a seismic mount or if you just need some heavier constraining within the load cell mount itself. Outside, you need to take into consideration the center of gravity, attached devices, and also wind. Wind can be a big factor, and there are other maps that show where we have a higher propensity of wind in the U.S. That needs to be taken into consideration when deciding which mounts to go with. Pharmaceutical applications have their own specific needs. The cells pictured are designed especially for ultra-clean applications. The finish of the cells are optimized to reduce the ability of foreign contaminants to gather, whether it's on the mount itself or on the cell. You notice there are very few vertical or horizontal surfaces for anything to adhere. Another type of specialty load cell, it incorporates an O-ring to seal the contact surfaces between the weighing module, the container leg, and the weighing foundation. Specifically designed between the silicone cover and the connection plates ensure reliable sealing of the dust and water-resistant internal space. The weighing module can be installed directly on the foundation or in connection with the optional mounting plates. You notice the picture there where we have one on the floor and one on the mounting plate. Instrumentation comes in many forms from many different manufacturers. The three most common formats are transmitters, indicators, and controllers. The transmitter does exactly what it says. It takes the weight data and transmits out on a customer-selected field bus. That could be Modbus, Ethernet, TCP, IP, Ethernet IP, DeviceNet, Profibus, or simply RS-232. The requirements of these is quite simple across the entire range. They must have the ability to amplify the low current signal, must have an A/D capable of very high precision, and must be able to communicate with process controllers in the field. Designing considerations for tank and silo weighing. What is a tank scale? A process vessel or tank plus the load cell transducers. What you have right here is a tank scale in front of you. What can I expect out of a tank system? What is the difference between accuracy and resolution? And also, do the components I choose need to help determine the accuracy of the system? Most importantly, and most times overlooked, is the piping considerations when talking about a tank and silo system. Anything that is installed on the tank that prevents the free motion of the vessel will reduce the accuracy of the system. Rigid tank-to-tank interactions will cause each tank, will cause fluctuations from one tank to another. They're attached to. Any piping should also be fixed with the same support as structure shown above. The rigid piping you see on the tank on the right needs to be replaced with a flexible piping. The flexible piping you see in the center is basically rigid piping because all the flex has been taken out of it in the installation. And rigid tank-to-tank connections can cause a problem as one tank may drag down the other two. Avoid hanging it from a floor where the floor may vibrate above, like a mezzanine where you have piping attached to that where either equipment or people could walk across and cause an introduction of weight changes in the vessel contained below. There's an example of a perfect one. In a perfect world, this would be how we'd set it up. Shoulder-mounted tank sticking through the floor with long horizontal runs from the tank and the piping. System performance, what can I expect? Accuracy versus resolution. Components, how do they matter? What factors my accuracy? A number of different questions that we're going to go over in order to decide how exactly to install our tank system. How accurately can my scaled tank be? The system is theoretically capable at the same accuracy as the weighing equipment that's installed. If you have a 0.5% load cell, you should have a system that's 0.5% in a perfect world. Unfortunately, we have issues when it comes to tank and vessel systems that cause for some ambiguity in what that final number can be. The type of piping that the customer is using, structural supports, other vessel interactions, if there's a mixer or any kind of motor that's mounted to the vessel itself, and low resolution instrumentation. Are they using a high resolution process controller? Accuracy is determined by the weighing vessel, by the weighing terminal and the weighing modules and the vessel itself. The vessel is the key component in this mix. Variations on mounting, connections, and environment will affect the accuracy of the system. Just get the rest of it out there. Resolution is determined by the weighing terminal's ability to discriminate small changes in weight and display it. This ability to see small changes in weight is often mistaken for accuracy. So there is a functional difference between resolution and accuracy. Scale can be, have very high resolution, but its accuracy could be off because for some reason the interaction of the piping on the vessel could be causing some fluctuations at the very high end. Okay, repeatability, the device's ability to constantly display the same weight each time it's applied. And of course, we just covered resolution. Okay, tanks that are installed directly on mezzanine structures are subject to problems such as cross interaction. As the tank next to it fills and empties, mezzanine floors flex. It can also be caused by people walking next to the vessel, vibration from nearby equipment, and many other factors. Another example of tank-to-tank interaction is shown on the top left here. A properly designed system would include an independent foundation and structural support for the weighing assemblies. If you have an application where high resolution is important to the customer, then adding these extra structural members will definitely improve their resolution and the output of the weighing system. Vessels on steel structures. As you can see here, deflection can cause the tilting of load cells. Anytime the load cells will tilt, you can have an introduction of an erroneous weight signal. The heavy tilting has an impact on the accuracy. Deflection must be equal on all sides. They're looking for a straight vertical load. Provide a rigid foundation that does not deflect under load. This is a pretty straightforward picture. They want to make sure that there is actually something under the vessel for the cells to press against. The picture on the right, as being as comical as it is, the picture on the left would be the best application for the load cells themselves. Weighing frames, design of a support frame. On the left, you can see the frame as looking at it from the top. You can see how it's pretty good. You can have the 4 load cells mounted on the outside perimeter of the system. But the one on the right shows that each one of them is actually being supported better and is providing more rigidity for the actual base itself. Weighing frames should be made in the stiffest way possible. Additional beams reduce the bending and therefore increase the accuracy of the entire system. All right, how many legs are ideal? The number of weighing modules required is dependent upon the design of the vessel. 3 legs will always be the most efficient design. It ensures the weight of the vessel is equally dispersed across all 3 legs. Although we all know that 4 legs is the most common design. The design with 4 legs, actually the more legs you have beyond 3, requires additional installation time due to the leveling required to ensure you have an equalized load on each module. Design of the vessel body. If you're going to use 3 legs, ensure that the legs are supported enough to hold the maximum capacity of the load. Another use of load measuring equipment is the level by weight method of calculating the volume of liquid material in a vessel. And I say liquid. The level by weight functionality is extremely good with a liquid product, but when you get into a dry product, because of the fact that you can have settling on one side of the tank versus an even dispersion of the product, it's not as accurate. It can still be used, but we wouldn't recommend it for a dry system. This is especially valuable in situations where other measurement equipment has failed to yield acceptable results. If for some reason the product in the tank has a foamy consistency to it, sometimes radar doesn't work as well as the customer would hope. And if they don't have room or don't choose to add any type of glass or any other type of leveling, then the level by weight is a great system. It's highly affordable, and we'll cover a couple more here. Pivot weighing system level sensors can be used on 3 or 4 leg systems when incorporating pivot points on the opposite legs from the load cell. This method provides an electrical representation of the level of the tank, but it does have a much lower accuracy than a full, in this case, 3 load cell system. If the customer is looking for a 1 to 2% accuracy and just knowing the weight of the volume of product they have in the vessel, then the level by weight system will work great for them. You don't always have to have the pivots on the back 2 legs. If you have just a 3-leg system, the 2 in the back can remain bolted securely to the floor, and the 3rd leg can be raised and set on top of a very low-profile sensor made by Sartorius Intec in order to provide them with an accurate representation of the level. Okay, the tank system. We've covered a number of different things. Let's kind of bring them all together. The tank system includes many factors. The classification of the area to be installed. Pipes need to be connected with flexible connections. This allows the vessel to move without restriction. If the load cell mounts do not have built-in constrainers or check rods, then they need to be added to the system in a manner that will restrict horizontal movement, but not the vertical. Side forces, like we discussed earlier, like wind and seismic matters, always need to be considered when designing a system. Most importantly, accessories, which are the most overlooked component, like mixers and other components, needed to be added to the overall weight of the system and seriously taken into consideration when designing an accurate tank and vessel system. A couple more examples of pipes and connections. Stiff pipes can have an influence due to the weighing result. Liquids in larger pipes can also have an influence, and they can appear as if they're actually in the vessel. So that's why it's best to have the longer vertical runs connected with the flex connection. This illustration shows how certain mounting kits are designed with environmental and application needs in mind. This vessel is outside in the wind with a mixer mounted internal to the tank. The constrained mounts will restrict axial forces while allowing the vessel to expand and contract with changes in temperature. Mounting kits with constrainers protect from structural damage and weighing errors. Depending on the number of legs and the forces to be expected, the configuration can consist of constrained and non-constrained mounting kits. For vessel scales with 3 legs, 3 constrained kits are generally recommended. For vessel scales with 4 legs, 3 constrained and 1 non-constrained is recommended, simply because it will avoid any type of binding within the system. A wind and earthquake calculation tool can be used to support the selection of the particular mounting kits. For best results and highest accuracy, it is very important that the mounting kits be installed with the top and bottom plates level to one another directly under the vessel foot. Floor must be even. Small slopes will affect the result. It is very important that these are shimmed so that they are completely level to one another. Interesting. Thank you very much, everybody. I appreciate your time. I know we kind of went through it quickly, but I wanted to make sure that we got all the information out in a really efficient and timely manner. If anyone has any questions, I would sure love to hear them.
We'll give them a few minutes to get some questions pulled together. In the meantime, I'll thank you for the presentation. Do you want to talk a little bit about the difference between matched load cells and non-matched, Jim?
Absolutely. To quickly cover those, so if anyone would, the difference is when, and we'll speak directly to the Sartorius Intec load cells. When they leave our factory in Germany, they are exact matched to have an output of 2 millivolts per volt on the 6211 canister compression cells and 1 millivolt per volt on our 6201 large canister cells. And when I say they're exactly matched, they are that. They are put under load, and the voltage is checked, and certain resistors are added to within the actual strain gauge on each individual cell before it leaves the building, so that they are factory matched to have the exact same output every single time you order one. The advantages of that: well, I can install 3 load cells in a system, and I won't have to calibrate it because I know exactly what my span voltage will be. I know that at full load, I will have 2 millivolts per volt coming out. So I can punch that into my system, and I have a very accurate representation of the weight. Second advantage is there. You can have, if a load cell for some reason, the load cell cable gets cut, or the cell gets hit, or for some reason fails, you can take it out, put a new one in, wire it right back up to our third advantage, the summing box, and the system will be running perfectly as if nothing had happened. The third advantage of the summing box is exactly that. It is a summing box. It is a place where the load cells come together and leave on the home run cable. There's no trim pots. There's no electrical components. There's nothing to induce noise. There's nothing in there that's going to be affected by liquids. It is simply a place where the wires come together because they're all matched. There's no reason to adjust them. If you had a standard load cell system, when a standard cell leaves a factory, I'm not going to pick on anyone in particular, it will come out with a load cell sheet telling you what its voltage is when it reaches its full deflection. That voltage can be different and will be different for each load cell that manufacturer ships. Now, when you get a system that has 4 load cells in it, you put those 4 cells under your piece of equipment, you're going to have a thing called a junction box. And within that junction box, each one of those load cells is attached to its own individual electrical circuit that you then have to use trim pots in order to adjust to balance the signal on all 4 load cells, because otherwise one is going to read higher or lower than the others. Having all those electrical components within the summing box is going to could potentially induce noise into a system, reducing the accuracy. You also have issues that if moisture does penetrate into the summing box, it's going to affect those electrical circuits, and it's going to cause an error in the signal. And most importantly, if something happens to that load cell in the system, when it's replaced, you will have to recalibrate the system, because you have to reconnect that to the junction box, adjust the trim pot there to match the other 3 signals, and then you'll have to recalculate the span using a full weight on that vessel in order to get an accurate weighment. Hope that covers it.
It does. Having been in a lot of plants myself, a lot of people will hire an outside source to do calibration on their load cells. Is that necessary with the Sartorius load cell because of the matching?
Well, there's 2 questions there, just so you know. Is it necessary? No, it's not necessary by Sartorius' standards. But each facility, each customer is going to have their own standard operating procedure, and if that procedure requires them to calibrate it, then we do not override that. But to have an accurate system, we do not need to be calibrated. It's completely on the up to the customer if their procedure requires it.
Right. Okay. The only question we have so far is, will this presentation be posted on the web? Absolutely. It may even be done by the end of today. We'll make sure that we send out an email that fills people in as to when it's available. We'll keep waiting for other questions, but I'll start to wrap it up. Jim, thank you very much for your presentation. Going back to your service to your country, I'd also like to thank you for your service. If you have any specific application questions, feel free to give us a call at 800-9-LESMAN or 800-953-7626. If you don't know your account manager, feel free to ask for me, Mike DeLaCluse, and I'll make sure to get you taken care of. Jim, I'm going to take over the presentation real quick and flip up this. Does Sartorius do their own calibration? It's one of the questions that just popped up.
No, we have partners nationwide that are certified, because there is some traceability when it comes to the calibration weights that are used in each state. It's different regulations. The scale partners that we have distributed throughout the U.S. have their weights certified in their individual state. So if you need to have a calibration done the most efficient method to do is to have someone local to you that we work with and we've trained do the calibration with certified weights that can be traced all the way back to the standard that that state uses. But we do not do our own service and calibration, no.
Yeah, we know who some of those sources are if somebody needs them. So you can contact Lesman and we'll get you set up. As we do wrap it up, if you want to know more about the technologies we supply, please follow us on social media. Dan's blog is very active and has tons of great tips. All of our webinars are posted both on our website and on our Lesman Instrument Code YouTube channel. There's, I don't know, 60 or 70 different videos out there at this point on all sorts of different technologies and at all different levels, so you can sift through those. If you want to know when something new is posted, please follow us on LinkedIn or Twitter because we do send out a note when something is posted. Our next webinar coming up, following on the weighing theme, just doing it a totally different way, is going to be Eric Heilweil, Product Manager for Siemens Coriolis, and he's going to talk about custody transfer, and that's going to be on Thursday, June 2nd at 9 a.m. Webinar invitations will be coming through an email. If you'd like to, you can also easily sign up on our website under the Training Center. Jim, I don't have any further questions, so with that, we'll wrap it up. Thank you very much. Audience, thank you for your time, and Jim, thank you for your presentation.
Thank you very much, Mike. It's nice to be here.
Yep. Bye.